Okay, another one with circular cross sections, and again, as with the last example, example 5, this shouldn't say the base because the base you might think of as, well, this one doesn't really have a base to really speak of, but we want to say that something about the diameters are along here. So it has diameters in the xy plane, and the cross sections perpendicular to the y-axis are circles. Okay, so here we go. Let's, as with always, lay this out. So the region above bounded by y equals 1 half x plus 2, y equals negative 1 half x plus 2, and x equals 4 it has the diameters of circles such that of a solid where the circles are perpendicular to the y-axis. That's important, y-axis. What is the volume of the solid? So let's look and see what this looks like first of all. If I were to lay this out a little bit, so it's an interesting shape. So if I take any cut perpendicular to the y-axis, we have this plane perpendicular to the y-axis. It will end up being a circle, not just a semicircle, but the entire circle. And we can see that any one of these will be circles, but we don't really have a cone this time. We have what's sort of like two cones stuck together at their bottom, but it's also not a right cone, so, but that's the shape that we have. And this right here measures our diameter. But if we look, so we have this circle, we get a diameter, we know we need a radius, we know the area in terms of a radius is pi r squared. But we look and our diameter is determined as the x distance in terms of some y. And we're going to want y to go from 0 to 4. We have functions of y in terms of x, so we need to actually look into that. Another issue is I will actually need two integrals. The first one I can go from 0 up to 2, and that uses this first function. But then the second one goes from 2 up to 4, and that uses this second function. So I need to do a few things here. First off, I need to solve both of these for x, because I want to find the x distance, and it's changing in terms of y. So let's do just that. So subtract 2, multiply by 2, x equals 2y minus 4. Subtract 2, multiply by negative 2, and we'll get x equals negative 2y plus 4. Okay, and now let's find the diameters, and let's call any diameter in this first section diameter 1, and then let's call any diameter in this second region diameter 2. So diameter 1 will equal the bigger function, which in this case is this vertical line at x equals 4, so 4 minus this curve, which is going to be negative 2y plus 4. And hey, this is pretty nice. The 4's cancel, and I'm left with 2y. And hey, that's even nicer. The radius 1, is half of that, which is just y. That's great. Okay. This other diameter, this other section, diameter 2, the outside function is still this vertical line x equals 4. This inner function is determined by this 2y minus 4, so I get minus 2y minus 4. Not quite as nice as previously, because the 4's don't cancel, but I will get 8 minus 2y. And that means that my radius is 4 minus y. Okay, and so this is radius 2. And that means that I'll have two area functions in terms of y. My area 1 function, I'll go straight to them in terms of y. We know the area of a circle is pi multiplied by the radius squared, but in this case the radius for 1 is y, so pi times y squared. My second area function for this second region up here is still pi r squared, but my second radius is determined by 4 minus y squared, so I will end up getting pi multiplied by 4 minus y squared. I don't really have room right here, so I'll just say, okay, 4 minus y squared. I get y squared plus 2 times 4 times negative y, which is minus 8y, plus this term squared, plus 16. Okay, and now we know that the volume of this entire figure will be made up of the sum of the integral from 0 to 2 and the integral from 2 to 4 of the respective area functions. So volume equals the integral from 0 to 2 of pi y squared dy plus the integral from 2 to 4 of pi y squared minus 8y plus 16 dy. And that will equal, and I'm going to go pretty quickly because I'm running out of space down here. I'll take the pi out to the front, so I'll have pi, and I'll take the antiderivative of what's left, so I'll get a y cubed over 3 evaluated from 0 to 2, plus, again, I'll take this constant multiple pi out to the front, take the antiderivative and get y cubed over 3, minus 8y squared over 2, which is going to be minus 4y squared, plus 16y, evaluated from 2 to 4. And usually, in all these problems so far, I was able to just ignore this 0 for all intents and purposes, but now I have this 2 down here. I have to make sure I do that correctly. So this will equal pi multiplied by, let's see, 2 cubed is 8 over 3, minus 0 cubed is 0 over 3. I'll put it in there. Plus pi. Now, I know that I should get the same value out of here that I got in there because the objects are just reflections of each other over the plane y equals 2. But let's go through the process and see it. So carefully now. 4 cubed is 64 thirds. So 64 over 3. 4 squared is 16 times 4 is 64. 16 times 4 is 64. Hey, that's nice. I like that. Wish that happened more often. Minus, and I put in the 2, and I get 2 cubed over 3, which is 8 over 3, minus 2 squared is 4 times 4 is 16, plus 32. Okay. So let's go through and see what we can do here. These cancel. Let me send this through. So I get plus, minus, plus, minus. Let's see, so 64 thirds minus 8 thirds gives me 56 thirds. These will give me a minus 16. And this is going to be then equal to, so 16 is the same as 48 thirds. Let me write that right here because I don't have room. So 16 times 3 over 3 gives me 48 thirds. And hey, by fraction magic, 56 thirds minus 48 thirds gives me 8 thirds. So I get 8 thirds pi for the second derivative. I get, second integral. I hope I didn't say derivative throughout this video. I get 8 thirds pi for the first integral. The volume is equal to the sum of those, which is equal to 16 pi over 3.